Okay, I want to marry natural pattern and symmetry and to get symmetric pattern. So natural patterns, they happens in nature and they are described by physical laws. They are rarely symmetric, but previous talk, sometimes they are, and I have few examples of symmetrical patterns in these slides as well. And symmetrical patterns, they are usually handmade or man-made. So we want to have, starting from a natural pattern generator, it is a gray-Scott reaction diffusion equation, and it is very nice equation which exhibit a very wide array of different patterns. And I will show you, these are like fast-growing worms. It is the same equation, different set of parameters in the equation. These are parallel waves. They are initially smooth and getting very unstable. And these are set of forming like maze, static maze. And this here we have how static spots are formed. And these are very interesting set of patterns. It is new gliders discovered by Robert Munafa. He is here somewhere. Thank you, Robert. And here is very nice spiral waves. And it is all the same chemical system, which is pretty easy to simulate, all these simulations. So how we going with arbitrary patterns we are getting from gray-Scott reaction diffusion to make it symmetrical? Okay, first start with a simple group generated by three mirrors, reflection in the mirrors. These reflections give us tessellation of the whole plane by triangles. We fill each triangles with a pattern from inside of fundamental domain, and we are getting nice symmetrical pattern, and we can run the simulation, and it is like kaleidoscopic effect, which we are very familiar with. Let's get more complex group, which is generated by rotations. So we are going the same way, doing this simple symmetrization, filling each tile with a pattern from inside the fundamental domain. Wow, it is not looking good. It is like broken mirror, and animations still have these ugly discontinuities. And we want to get rid of these discontinuities. So analysis of wallpaper groups give us that all wallpaper groups generated by reflections, they are works reasonably well. The rest, certain groups are not well. But let's look on simple symmetrization algorithm. We are doing like this infinite loop of simulation step, simulation step, simulation step. After each step, we are doing symmetrization and displaying. And kind of simulation is separate from symmetrization. Instead, we did very simple modification. Did like, I call it symmetric simulation, SymSim. So after each simulation step, we're doing symmetrization and feed result of this symmetrization back into simulation. So we're kind of pushing system into symmetrical solution. So let's see how it works for this ugly example. Okay, after 50, 60, 70, 100 steps, there is no discontinuities in the symmetry whatsoever. And this is animation, how it looks like. Looks pretty well. So now I will show a few examples. So this is one of my favorite examples. Initially ugly patterns slowly turn into beautifully animated spiral waves, and after that it got into this stable condition, it will go on forever. These are set of these gliders. They are like it is juggling. I ask if jugglers can do this. Somebody promised to do jungle with 300 balls yesterday. Another example, it is spinning windmill made out of these long worms. Another example, it is spirals, this spiral pattern put into a different symmetry group. It is also periodic solution which will go on forever like this. no, sorry, it is not periodic, but it getting there. It is ugly tentacles which are kind of oscillating and going back and forth. I was thinking maybe they will go on forever like this, but maybe eventually they will stop and kind of these tentacles will collapse. But they can go like this for a long time. These are spinning worms. It is kind of like, again, these long worms, I kind of bend them and they continue this dance. Imagine yourself inside of this labyrinth which is kind of changing its shape. Kind of, you have to be very fast to get out of it. And this approach works perfectly well for any system. Now it is the Ginzburg-Landau equation, which is describing superconducting condition, and it have like this positive and negative parts. They kind of interpenetrate each other. And this simple SIM has nice properties, but the nicest properties is that it actually implemented as a HTML application in JavaScript and run inside of web browser on any available platform. And this is like website where there are like bunch of videos and interactive applications for two different equations. That's it. Thank you.